Hello, welcome to EEE 41 Lecture 13 about Schottky diode IV and small signal capacitance and practical ohmic contacts. Our objective for this lecture is to draw the energy band diagram of an MS contact under applied bias, differentiate the operating principle of MS junction Schottky diodes from PN junction diodes, identify the parameters affecting the reverse saturation current in Schottky diodes, and lastly, identify considerations for practical ohmic contacts. Let's start by discussing qualitatively the current flow in a Schottky diode. Here we have an MS contact, a rectifying MS contact with an N-type semiconductor. From the previous lecture, we have identified that this case is a rectifying MS contact or a Schottky diode by looking at the energy band diagram from the point of view of majority carriers, in this case, the electrons. So here electrons sees a rectified barrier from both sides, and therefore this one is a rectifying MS contact. Note also that this energy band diagram right here is the case when the device is in thermal equilibrium or when there is no applied voltage and there already exists a built-in voltage within the device. Now, if we apply some non-zero voltage, we need to define first the polarity. So we'll use this notation here where we will assume that the semiconductor side is grounded and the applied voltage is at the metal side. Now, if we apply a positive voltage at the metal side, then the voltage at this side is higher, which means that the Fermi level at that side must be lower than the Fermi level on the other side. From relative to the Fermi level of the metal, the Fermi level of the semiconductor actually increased, and that led to this less bent energy band diagram at the semiconductor side. And its bending is actually less by QVA. So we have this term minus QVA. On the other hand, if we apply a negative voltage, VA, then the Fermi level at the metal side will be higher by QVA relative to the Fermi level at the semiconductor side, and that actually leads to a more pronounced bending at the EBD at the semiconductor side. So note that this time VA is a negative quantity and therefore this bending is larger than its equilibrium value. Now let's say we want to identify which one of these two cases is or can be considered as forward biased or reverse biased. We can actually identify that by looking at how the current flows. But let's start with the flow of carriers when we are in equilibrium. So at the metal side, we have a lot of electrons above the Fermi level, and we also have a large amount of electrons at the N-side semiconductor. Now, for the material to reach thermal equilibrium, then Jn must be equal to 0, and that there must be no net flow of electrons in the device. From the metal side, some electrons are able to cross the Schottky barrier, and there are also some electrons that are able to cross the barrier from the semiconductor to the metal, and these two currents must be exactly equal to reach thermal equilibrium. Now let's see how this bending affects the interaction of the flow of electrons within the device. Remember that for Schottky diodes, the current is actually dictated by the flow of majority carriers across the junction. Now it turns out that for our setup, our N-type Schottky diode, where the applied voltage is at the metal side, that applying a positive voltage forward biases the device. And how does that happen? Let's look at the interaction of majority carriers or electrons at the two sides. So here we still have the same amount of electrons, and even if we change the bending at the semiconductor side, these electrons still sees the same barrier in crossing from metal to semiconductor, and thus the electrons flowing from metal to semiconductor does not change. However, at the semiconductor side, since we decreased the bending, then the barrier that this electron sees in crossing from semiconductor metal to the metal actually decreased, that aside from the original electrons being able to cross the junction, there are now more electrons that are able to cross the junction. This leads to a net flow of electrons leftwards, and a net electron leftwards lead to a net current that is rightwards, meaning we have some positive current, and that actually um, represents this one. And it is actually increasing exponentially with the applied voltage, since as we increase the voltage, the less bending happens on the semiconductor side and more electrons will be able to cross the other side and overpower the flow of electrons from metal to semiconductor. So we say that for forward bias, the majority carrier diffusion from semiconductor to metal dominates. However, for the reverse bias case, where we increase the bending at the semiconductor side, from the point of view of the electrons from the metal side, again, the barrier does not change. So we still have the original flow of electrons in equilibrium. However, for the electrons at the semiconductor side, the barrier actually increased, and most of them are now not able to cross the junction. So in this case, the current is dominated by this component here. So there is a net flow of electrons from metal to semiconductor, from left to right, and that leads to a current that is leftwards, or from semiconductor to metal, and so we get this negative current here. Now, why is that when we increase the negative voltage or increase the reverse bias, the current does not change? Now, note that if we increase the reverse bias, then the bending at the semiconductor will be steeper, and so the electrons will at the semiconductor side will still not be able to cross, but the electrons from the metal will still be able to cross, although the barrier it sees does not change, so the current will not change approximately, and that leads to this reverse saturation current. Now let's take a look at the depletion layer width when we apply some voltage. This expression here is the same expression that we will obtain if we take a look at the charge density, integrate it using the Poisson's equation to get the electric field, and integrate it again to get the voltage. This result is the same as the one we had in the previous lecture. However, this time we'll use the boundary condition that at x is equal to 0, the voltage is minus VBI minus VA. Remember that in our previous lecture we have decided to define the voltage to be 0 at the semiconductor side, and in that lecture we used that the voltage at the metal semiconductor interface is minus VBI. However, this time that voltage will be lower by VA, so we add VA, and that actually increased from minus VBI to minus VBI minus VA. Now we can use that boundary condition and substitute to this expression right here. So when we evaluate at x is equal to 0, this one disappears, and the voltage at x is equal to 0 is equal to negative quantity VBI minus VA. With this, we can actually solve for W. So W is simply equal to the square root of VBI minus VA times 2 epsilon s over Q and D. So this negative sign canceled with this negative sign. And so we note that the depletion with W decreases when we increase VA. And note that when we increase VA, this is towards forward bias. So just like in our PN junction diodes, when we forward bias the device, the depletion region decreases. So the reverse is true. When we reverse bias the device, the depletion width increases. In terms of the doping concentration, the width decreases with increasing doping concentration, which is also the same result we obtained for PN junction diodes. Now let's consider the case for a Schottky diode with a p-type semiconductor. We'll use the same notation where the semiconductor is grounded and the metal is the one where we apply the voltage. If we take a look at the charge densities within the material, we know that there will be some depletion region at the P side, and the exposed acceptor dopants will give a negative charge density, and a positive charge density of equal magnitude will appear at the metal side. If we use Poisson's equation, then we can integrate the charge density to get the electric field. So we'll start at 0, integrate some positive area, and then integrate negative area until we get back to the 0 electric field point. We can then integrate this one and apply a negative sign to get the voltage. However, since we have defined that the voltage is 0 at the flat band region of the semiconductor, then we'll actually get this plot right here, a decreasing plot, since we are integrating with a negative sign. And this one would be VBI plus VA instead. Since we are defining VBI to be always positive, and if we take a look back at the energy band diagram for a Schottky, p-type Schottky diode with a rectified barrier for holes, when we flip the EC, we should get this plot right here. And when we apply some voltage, we'll add this plus VA term. Now, performing the integrals, we will actually end up with this same similar equation, although this time there is no negative sign since we started with a flipped charge density. Now we'll apply the boundary conditions that the voltage at x is equal to W is 0, and that the voltage at x is equal to 0 must be equal to VBI plus VA. So if we evaluate that at x is equal to 0, then this one disappears, and we can equate this to VBI plus VA. And so solving for W gives us that W is simply equal to the square root of VBI plus VA times 2 epsilon S over Q NA. Now with this expression right here, we note that W increases when we increase VA and W decreases when we increase NA. Now this one is similar in form as we had in the previous slide, although this one is the opposite as the one we had previously. And actually it turns out that when we plot the IV curve for this Schottky diode, we'll actually get this one, which looks like similar to the Schottky equation but flipped with respect to the origin. And why is that the case? Note that this Schottky diode acts like a diode oriented this way. And since we are defining the voltage to be plus here and minus here, and we are also defining the current to be entering here, then we will actually have to flip the voltage and the current in the original Schottky diode plot. So if we have our original plot, if we flip the voltage, then we'll flip along the x-axis, we'll get this one. And then if we flip it at the for the current axis, then we'll get this plot right here. And so this IV curve is actually a result of the notation of the voltage and the current. However, we'll still use that the semiconductor is grounded to be consistent with our assumption that the voltage is 0 at the flat band region of the semiconductor. Now let's also take a look at what happens with the holes when we apply some voltage. Let's consider first a positive voltage. So when we apply a positive voltage, the Fermi level at the metal actually decreases with respect to the Fermi level at the semiconductor and end up with an energy band diagram like this. Okay, so the Fermi level at the metal is a bit lower with the applied positive voltage. Originally, the flow of holes is balanced, but applying a positive voltage actually increases the bending, which increases the depletion width and prevents the holes from the semiconductor side to cross to the metal. And so we are left with this constant flow of holes from metal to semiconductor, which is a small value and a positive value. So even if we increase the applied voltage, the bending here increases, but the current will not change significantly. Now for the opposite case, when we apply a negative voltage, the Fermi level at the metal increases relative to the Fermi level of the semiconductor, and now more holes are able to cross the junction into the metal, which leads to a negative net current that increases with the applied negative voltage, and so we end up with this behavior right here. Now the current resulting from majority carrier electron or hole majority carrier injection over the potential barrier in an MS or Schottky diode is referred to as thermionic emission current. To establish the quantitative expression for the thermionic emission current, we treat an N-type device and focus initially on electron injection from the semiconductor side to the metal. Now the x coordinate is assumed to be normal to the MS interface and positive directed to the semiconductor. Now consider an electron entering the depletion region from the semiconductor bulk. It will only be able to cross the junction if it has enough energy beyond the barrier it sees from the semiconductor side, which is this QVBI minus VA. And so that electron will be able to cross into the metal if its kinetic energy, which is 1/2 mv squared, is greater than QVBI minus VA. And therefore, this electron must have a minimum velocity equal to this one. Okay, we apply an absolute value since this velocity is actually negative relative to our defined axis. Now, if we count the number of electrons that are able to cross the junction by having this specific velocity, then we can just multiply that and get this expression. So the current from semiconductor due to the electrons crossing the semiconductor to metal is equal to minus QA times Vx times N of Vx, where this N of Vx right here is the density of electrons per unit volume per unit speed, or velocity. So this is a density of electrons relative to velocity. So when we multiply that by the velocity, we get the density of electrons, and multiply by the charge of electron in area, then we get the current. This current here must be positive because of this negative sign right here, and we expect that Vx is negative. So we are consistent that the current must be positive since electrons are flowing to the left. Now this equation here only gives us the current when we have some specific velocity. To get the total current, we must also consider some other electrons that are able to cross with a different velocity. So we'll have to integrate across all different velocities that allow the electron to cross. So we'll consider from negative infinity to minus V min, since negative infinity means it has a high velocity but to the left. For a non-degenerate semiconductor, it can be shown that the density of electrons having a specific velocity is equal to this equation. Now, this one should be somewhat familiar in form, as it takes some of the constants and can be derived from the density of states. However, the density of states is in terms of density per energy, but we'll have to convert that to density per velocity. And so again, we have to integrate this equation right here from this negative infinity velocity to minus V min. And so we'll have to plug in this one as this function and proceed with the integral. Now the result of the integral is actually equal to this one, where we see some constant multiplied by, this whole constant here multiplied by EQVA, which simply tells us that when we increase the applied voltage, then more electrons are able to cross the barrier. Now, to make the equations a bit simpler, we'll just isolate this term right here and say that that must be the reverse saturation current density Js. Now that Js is equal to this one. So we have the t squared term, the e raised to minus phoebe term, and then this term right here should actually represent this term. So when we evaluate with all the constants, then we'll be left with this one. Although we have written it in terms of the Richardson's constant, where the Richardson's constant is a naught 4 pi q k squared, 4 pi q k squared, m naught over h cubed, m naught over h cubed. However, this one is in terms of mn star. So we'll have to multiply by m naught over m naught and factor out mn star, absorb the mn naught in the numerator, and plug that in for the Richardson's constant. So this 120 here is in amperes per cm squared, Kelvin squared. Now note that in the reverse direction, the electrons see the same barrier phoebe from metal to semiconductor, and therefore changing the bias will not affect this current from metal to semiconductor. And that must be exactly equal to the current from the semiconductor to metal at VA is equal to 0 to reach thermal equilibrium. And therefore we'll just have to evaluate this at VA is equal to 0, and therefore this current from metal to semiconductor is ISM negative, evaluated at VA is equal to 0. So we have A Js e to the 0, which is simply 1. So we'll end up with this A Js. So this IMS is this ISM evaluated at VA is equal to 0 with a negative sign. Now the total current is the sum of the current from metal to semiconductor and semiconductor to metal. And so we have to add this one with this one. And so we can factor out AJS, and we'll be left with AJS times e to the QVA minus over KT minus 1. And we have just shown that indeed the current for our Schottky diode must follow the same form of the Schottky diode current model. Now, aside from the cross-sectional area, the other important parameters for the reverse saturation current is temperature and the Schottky barrier height. Now, increasing the temperature gives more energy to the electrons, which allows them to cross easily to the other side. Okay, so this reverse saturation current increases with temperature. In terms of the barrier height, when we increase the barrier height, then less electrons will be able to cross. Then this Js right here actually decreases with the barrier height. Now it actually turns out that the IS, or reverse saturation current of Schottky diodes, is around 10 to the 3 to 10 to the 8 times larger than that of a PN junction diode, depending on Phoebe. This makes Schottky diodes preferred for low voltage, high current applications. So consider if we have a large IS, so for the same applied voltage, we'll get a larger current. So for the same applied voltage, the MS Schottky diode achieves a larger current. Now, if we have a requirement to give out a high current, then for the same current, then the MS Schottky diode will need a low voltage or can be operated with a lower voltage. Also, Schottky diodes are preferred if you want lower power consumption when using the diode as a switch at the on state. So for example, you have a switch which turns out to be you want to implement that as a diode. So the switch actually have some effective resistance. Now, if I have some high current here that I want to pass, then ideally this resistance here is a short, an ideal switch, and that would dissipate zero power. Now, for the same current, the higher the voltage dropped at this resistor, the higher the power dissipated or wasted at this device. But since Schottky diodes can support higher currents at lower voltages, then the Schottky diode will consume less power for the same amount of high current or current basically. Although the disadvantage is that since it has a larger IS, then it has a larger reverse leakage. Let's have a short review of the Schottky IV characteristic. In a Schottky or rectifying MS contact, charge is stored on either side of the MS contact, and the applied bias VA, defined here, modulates this charge. It modulates the amount of charge and the voltage drop across the semiconductor depletion region. The flow of majority carriers into the metal varies exponentially with VA. And it is given by this equation where the reverse current density is given by this equation, where this is the Richardson constant and depends on temperature and the barrier height. Now let's discuss the small signal capacitance in Schottky diodes. So if an AC voltage small VA is applied in series with a DC bias VA, then the charge stored at the Schottky contact will be modulated at the frequency of the AC voltage. Now, the average charge will be determined by the DC voltage or the average voltage, and applying some small signal voltage will cause the depletion width to vary around that value and causing some small signal charge to be moving around this depletion region with. Now, it would lead to some capacitance where we'll use this I is equal to CdV over dA. But since I is equal to dQ over dt, then we can actually cancel this one and get that C is equal to dQ over dVA, meaning the small signal capacitance that we'll get is related to this amount of charge that we are getting for this applied small signal voltage. Since the charge is displaced by a distance W, then we can model the small signal capacitance as a parallel plate capacitance, and we can use epsilon A over D or epsilon A over W. So here we substitute the expression for W, given that we apply a voltage at our N-type MS junction. So we get this expression here to be equal to the capacitance of the Schottky diode. Using the same approach as with the PN junction diodes, we can square this one, get the reciprocal, so we get 1 over c squared, and get this expression right here, which turns out to be linear with respect to voltage and will be 0 at VBI. Now we can actually measure actual capacitance from our Schottky diodes at some reverse bias and plot the 1 over c squared values with respect to voltage. And if we get this plot, we can actually interpolate or extrapolate VBI, and from the slope we can get that the slope must be proportional to 1 over ND. So after we have done that, we were able to identify VBI and ND. Then we can determine Phi, which as we have said, cannot be expected to be always exactly equal to Phi m minus chi. So we can use this equation here, where QVBI is equal to Phi Bn minus EC minus EF at the flat band side, which can be observed using this illustration right here. So QVBI is Phi Bn minus EC minus EF at the flat band side. So here we copy Phi Bn, but EC minus EF is KT ln NC over ND. Note that we are not using ND over Ni, since that is since we are not concerned with EF minus EI. However, we can use an alternate expression for this one to be some EG over 2 minus KT ln ND over Ni. So now we discuss practical ohmic contacts. So in practice, most MS contacts turn out to be rectifying. Looking back at our discussion in the previous lecture, when we fabricate our MS contacts, regardless if Phi m is greater than or less than Phi s, most of the MS contacts actually become rectifying, since the Fermi level at the semiconductor side is pinned around 0.4 to 0.9 below EC because of the interface states that are formed between the metal to semiconductor interface. So if we almost always end up with a rectifying MS contact, then how do we make an ohmic contact? So we can actually achieve an MS contact that easily conducts in both directions, practically an ohmic contact, when we heavily dope the semiconductor. So in this case, the MS contact is still rectifying by definition, but by heavily doping the semiconductor, the depletion width becomes so narrow that the carriers can tunnel through this barrier. To visualize that, let's consider the case for an N-type MS contact wherein the semiconductor is so heavily doped that EC is approximately equal to EF already. So at equilibrium, since EC is approximately equal to EF, then the Fermi level must be flat throughout the material. And so here we can actually see that the barrier is still actually rectifying, but since the semiconductor is so heavily doped, so ND is very large, then W tends to be very small. Also, Phi Bn is now approximately equal to Q VBI. Since EC is approximately equal to EF, then the bending here should be approximately equal to this one, VBN. Now, if we apply some voltage that is not equal to 0, so the Fermi levels are now not exactly aligned, then originally what happens or what we expect is that electrons at this side will not be able to cross the junction unless they have overcome the barrier height. However, since this barrier here became so thin, then electrons can actually tunnel through that barrier even when not achieving or overcoming the barrier height. So technically, this barrier here is approximately not there at the point of view of the electrons, which means that the electrons can actually easily cross the junction. And when the carriers can easily cross the junction, then this device actually presents a very small resistance. Okay, so we have this what we call specific contact resistivity rho sub C. Okay, so rho sub C is the resistance of a 1 cm squared ohmic contact. This contact resistivity is normally given in some ohm cm squared, and it is proportional to E raised to h times the barrier height over square root of ND, where h is this constant right here. So if we decrease the barrier height, then the resistance decreases, which is actually what we want for our ohmic contacts, although we don't have actually much control over this one. So we can simply increase the doping concentration to decrease the contact resistivity. So if we have some cross-sectional area, the resistance of that contact can be obtained by dividing by the cross-sectional area. So the larger the cross-sectional area, of course, the less the resistance. So now if we actually aim for a very small resistance, so since the resistance is small, then there will be so very little voltage drop across the contact such that VA is approximately 0 even if we pass a large current through the contact, meaning the properties of the material can be approximated by its thermal equilibrium value, since the voltage drop is only very small most of the time. So approximately speaking, equilibrium conditions prevail in our practical ohmic contacts. To summarize our discussion on MS contacts, we have this, we can follow this table right here. This one is the case for ideal MS contacts, where if the device follows the ideal analysis, when Vm is greater than Vs for N-type semiconductors, then we'll end up with a rectifying Schottky diode. So as a review, we draw the reference is E0, and exactly at this point we can see that the barrier height is equal to Vm minus chi. For the case when Vm is less than Vs, we actually end up with an ohmic MS contact. So again, we're looking at the point of view of the majority carrier. So for P-type semiconductors, when Vm is greater than Vs, we end up with an ohmic contact. when Vm is greater than Vs. But when Vm is less than Vs, we get a rectifying MS contact when using a p-type semiconductor. Since it is difficult to achieve a small barrier height, practical ohmic contacts are achieved by using heavy doping on the semiconductor side to make the depletion width very thin for carriers to be able to tunnel from one side to another easily. Now there is charge storage in an MS junction, which introduces some small signal capacitance, which can be modeled like a parallel plate capacitance. Plotting this with respect to voltage, or 1/c² with respect to voltage, allows us to characterize the device, get the doping concentration in VBI, and from VBI we can approximate the value of the barrier height. Okay, so that's it for this lecture. Thank you very much.